Hi everybody, I would like to thank the organizing committee for the invitation to give a talk at this important conference. My name is Paolo Ferrari of CPRA, Research Center for Animal Production in Reggio Emilia, Italy. The presentation I am about to give you concerns research activities of the Healthy Livestock project to develop biosecurity risk assessment tools to define pig and broiler farm tailor-made health plans. Healthy Livestock is a research project funded by the European Union within the Horizon 2020 European Programme for Research and by the Chinese Ministry for Science and Technology. It is coordinated by Hans Poedel of Wageningen Livestock Research in the Netherlands and involves internationally renowned experts and scientists from the European Union and China, working together to tackle antimicrobial resistance. 23 partners, including academia, research institutes, private partners and companies, are involved from China and Europe, 9 from China and 14 from 8 European countries. This is a 4-year project starting in 2018, so now Healthy Livestock is close to the end and most research outputs are going to be delivered and published soon in the next months. The main objective of Healthy Livestock is to reduce the use of antimicrobials applied to the pig and broiler industries in China and Europe, and the subsequent residues in the food chain and the environment, by reducing the need to use antimicrobials in animals through the improvement of their health and welfare without compromising productivity. A reduced need to use will lead to less usage, hence less exposure of microorganisms to antimicrobials and thus less emergence and spread of resistant genes and resistant bacteria to other animals and also people. 4 strategies have been investigated in this project to achieve the main objective in pig and broiler farms. The first one is the improvement of farm biosecurity based on biosecurity zoning analysis and further monitoring of animal health and welfare through animal-based biomarkers. The second is the improvement of animal resilience, or the ability of animals to adapt to environmental changes with minimal loss of function, by means of probiotics for improved gut health and through welfare improvement measures. The third strategy is the rapid detection of animal diseases through animal behavioral recording and behavioral early warning indicators. The fourth strategy is precision medication through optimal dosage based on pharmacokinetics and bioactive compounds of the traditional Chinese medicine. A specific work package is dedicated to the first strategy, the improvement of biosecurity conditions in animal husbandry. It is aimed at reducing the risk of pathogen introduction, exposure and spread on modern intensive broiler and pig farms in China and Europe, to the development and application of tailor-made health biosecurity protocols and health plans. 7 partners are involved in this work package, 4 partners from Europe, CPRA, Wageningen Research, INRA and VTN, and 3 partners are involved in China, DLHL, DBN and CAP. These novel tools and protocols can be used by farmers and their associated veterinarians in the future to control diseases and reduce the use of antimicrobials. Recent research shows that the currently available general health plans to control disease risk following a one-size-fits-all approach are not relevant to control diseases, and that a method to adapt general plans to specific risks in a farm should be further developed. This work package delivers the use of 2 novel biosecurity tools and protocols to assess systematically disease risks related to housing and management in broiler farms and pig farms to define farm tailor-made health plans, including biosecurity protocols and adapted to the farm-specific risks, and to monitor the risk mitigation by means of biomarkers, which are innovative animal-based indicators, enabling early detection of breaches in biosecurity and prediction of increased risk of disease occurrence. Two biosecurity risk analysis tools, also called BEATs, were developed, one for pig farms and one for broiler farms. The tools were based on two earlier development conceptual approaches. One is the BioCheck-UGent Biosecurity Assessment System, and the second is the FEO 3-zone biosecurity model. BioCheck-UGent focuses at the external biosecurity or risk of pathogens entering or escaping from the farm, and at the internal biosecurity or the spread of pathogens over the farm. The FEO 3-zone biosecurity identifies different zones on and around the farm. The red zone outside the farm, the orange zone inside the farm but outside the animal houses, which is also called the professional zone, and the green zone, or the animal houses in which pig or broilers are kept. And also the systems is focused on their interfaces between these three zones, or transition lines which are crossed by animals, workers, machines and vehicles. Based on the outcomes of the risk assessments, farm-specific animal health plans were drawn, tailored to the specific situation on the farm. For each zone and its connection with the neighboring zones, risks were identified and goals were set. With the help of an easy-to-use Excel scoring system, a tailor-made farm health plan was drafted. The draft plan is proposed to the farmer and the associated veterinarian, and the farm health also comprises advices for the redefinition of the 3 farm zones, for instance, or also hygienic measures per zone, hygienic measure for going from one zone to another, and implementation of biosecurity protocols. The biomarkers to monitor mitigation of biosecurity risks due to farm biosecurity improvements included direct and indirect signs of infection diseases, such as clinical symptoms and results of laboratory analysis for bacteriology, virology, serology, and the presence of stress indicators. Main aims of the biosecurity assessment tools are to raise farmers' awareness about biosecurity risks, to involve both farmers and associated vets in biosecurity analysis, and to recommend preventative options in case of non-compliance. Biosecurity analysis is carried out in 4 steps. In step 1, a schematic drawing of the farm location is done and risk zones are colored in red, orange and green. And all buildings, stables, storage sites, pathways for animals, workers and vehicles are identified. In step 2, all questions about risk factors are answered and relevant scores are given for different zones and transition lines. 113 risk factors were analyzed for broiler farms and 97 risk factors for pig farms. All risk factors for the transition from orange to green and the green zone were filled out for each broiler or pig house on the farm. In step 3, the overall scores for each of the 3 zones and 2 transition lines are analyzed in collaboration with the farmer and his associated vet, and possible opportunities for improving biosecurity are identified. Finally, an action plan with smart formulated preventative actions for strengthening of on-farm biosecurity is agreed and defined in step 4. The biosecurity assessment tools were developed and refined in a reiterative consultation process. They were presented and discussed between experts of disease causation, researchers, or disease control, field and official vets of the competent authorities, and of pig and poultry farming, representative of pig and poultry farmers, within 2 rounds of consultation in the Netherlands by Wageningen Research, in France by INRA, in Greece and Cyprus by VTN, and in Italy by CPRA. The table on your left is only an example of risk factors for the red zone of broiler farms, which is the external zone outside the farm. For instance, risk factors here are the poultry density in the geographic area in which the farm is located, distance to the nearest poultry farm, the shortest distance to public road with daily animal transports, the spread of poultry litter manure on surrounding fields, the presence of water ponds within a radius of 1 kilometer, and the presence of migratory birds route in the vicinity within a radius of 1 kilometer, and so on. Each risk factor was assessed and scored, and this was done for all risk factors of the 3 zones, red, orange, and green, and their transition lines from red to orange and from orange to green. At the end, 5 overall scores are calculated for each zone and transition line in terms of percentage of the maximum score achievable for each zone or line. The higher the percentage, the lower the biosecurity risk. This approach can also be used to benchmarking farms according to their overall scores, as done by the Biocheck Jugend assessment systems. This is another example of the risk factors for pig farms in the green zone, which is the pig houses, such as the risk of pig contact with other pig age groups, or with contaminated premises, or farm internal or external staff. Monitoring biosecurity risk mitigation was carried out by means of animal-based indicators enabling early detection of breaches in biosecurity and prediction of increased risk of disease occurrence. They potentially lead to the design of toolkits by diagnostic laboratories sold to veterinarians, advisors, farmers, or companies as a product for monitoring risk for farm management for assessment of innovations, for instance, new devices or technical protocols for biosecurity, or for food product quality standards, for instance, food chain actors and retailers willing to promote labels for health and welfare. To be fit for purpose, a biomarker should be an indicator of a biological process or pathological states, and it can provide information on current status of future risk of disease of an individual. It should possess key characteristics and qualities which will depend upon its intended use. It should be accurate, sensitive, and specific. It should be altered in the relevant disease and be able to discriminate between diseased and controlled populations, but also quantified reliably and reproducibly. For diagnostic purposes, it should ideally be obtained from readily accessible body fluids in animals such as blood, plasma, urine, sweat, or saliva, or other accessible materials such as air and feces. But also disease non-specific biomarkers and animal-based measures can be considered to monitor animal health and welfare. Selected biomarkers for broiler farms were foot pad lesions as indicator for animal welfare and health, and manure levels of Campylobacter analyzed in manure samples taken just before first thinning round, as indicator for biosecurity breaches. Foot pad lesions were assessed through visual scoring at slaughterhouse, according to the official method used across EU member states, in compliance with Council Directive 2007/43, using at least 100 feet of 100 birds per flock, scored on a 3 scale 0, 1, 2. Campylobacter infection was hypothesized to be higher in broiler farms with lower biosecurity. Campylobacter is also a zoonotic marker of public health importance, and manual sampling for laboratory analysis is non-invasive, adheres to good animal welfare practices, is repeatable, and does not require specialist equipment and or high level of expertise. Farm antimicrobial usage was calculated according to the DDD-VET methodology, and pre- and post-intervention economic and productivity data of farms, as well as pre- and post-intervention farmers and veterinarians' opinions, were collected by use of questionnaires. The protocol for pig farms is more articulated than for broiler farms because the production cycle in pigs is more complex with different phases for breeding, weaning, growing, and fattening. So 10 biomarkers were selected for pig farms. The first is cough, sneezing, and labor breathing scores for a farm representative sample of pigs as clinical symptoms for respiratory tract infections. The second was the PCR serology test for porcine reproductive and respiratory syndrome in pigs with symptoms of respiratory disease. And this was done only in those farms which were not vaccinated already from PRRS. The third was a feces score for a farm representative sample of pigs for the evaluation of enteric diseases in sows, piglets, weaners, and fatteners. The fourth was the feces laboratory analysis for E. coli in pigs with symptoms of enteric disease. And the fifth was the skin and plaque lesions in slaughter pigs as assessed at slaughter. Haptoglobin also was considered as a biomarker in serum and blood samples of weaners. It is an acute phase protein fraction considered as an unspecific health status marker. The seventh biomarker was cortisol analysis in pig hair. Cortisol is the main stress hormone and is considered as a biomarker for pig health and welfare. Also, the dihydroepiandrosterone in pig hair was selected as biomarker for pig health. It plays a role in immune system activation. It has anti-inflammatory and antioxidant properties and is involved in lipid metabolism. Pigs affected by stress show an increase in the cortisol level to stimulate metabolism and energy production, and a decrease in dihydroepiandrosterone. Bacterial load on pen surfaces after cleaning and disinfection in all-in, all-out system was also measured, and data about mortality rates for all categories of pigs. 40 pig farms and 35 poultry farms were involved in data collection, although farm recruitment and consequent farm visits were hindered by COVID-19 emergency. However, farms were visited at least 3 times during a 12-month study to assess changes in health, welfare and productivity, changes in biosecurity practices and health risk management according to the health plan output measures agreed with the farm managers and their vets, changes in antimicrobial usage according to the DDD-VET methodology to get comparable data from different farms and from different countries, opinions of farmers and associated vets about effectiveness of the biosecurity assessment analysis, the related health plans and protocols to monitor biosecurity risk mitigation, farm economic figures before and after the implementation of the health plans, and antibiotic residues detection in meat sample at slaughter and drinking water and manure sample on the farm. The implementation of health plans and visits on whole pig and broiler farms were completed last year, 2021, and results are being processed and are expected to be published in the second quarter of 2022. Thank you for your attention.